projects. In this video, we are going to explain about the project, which is a fine-grained object detection model for aerial images based on YOLOv5 deep neural network. Introduction of the project. The project addresses the challenge of recognizing multiple classes of fine-grained objects in high-resolution remote sensing images, which is a critical task in computer vision. Unlike natural scenes, remote sensing images present arbitrary object orientation, dense alignment difficulties, and complex backgrounds, making traditional object detection algorithms less effective. The accurate detection of rotating objects is particularly crucial for applications in military defense, intelligent transportation, geological disaster monitoring, maritime surveillance, and urban planning. The project discusses the limitations of the existing rotating object detectors, particularly the issues related to boundary discontinuity in predicting orientation accurately. The focus is on the importance of accurate angle prediction for successful detection of rotating targets in remote sensing images. The project acknowledges the deficiencies in the quantity and quality of existing remote sensing datasets compared to natural scene-centered datasets. Fine-grained object detection is highlighted as an essential for distinguishing similar targets and ensuring better generalization in the real-world scenarios. The project introduces a novel method which is YOLOv5 CSL as an improved version of the YOLOv5 algorithm specifically tailored for fine-grained object detection in aerial and remote sensing images. Key contributions include the addition of an angle classification module which is CSL for accurate estimation of rotating target angles, the incorporation of a self-attention mechanism to enhance the model's perceptual field, and the utilization of the latest activation function to reduce model parameters and improve practicality. Extensive experiments on public evaluation dataset, which is DOTA, demonstrate the effectiveness of the proposed method in aerial object detection. Objective of the project. The objective of the project is to address the deficiency of advanced object detection algorithms primarily designed for natural scenes and their limited applicability to fine-grained objects in remote sensing. The objective is to extend the usability of these algorithms to remote sensing object detection. The aim is to investigate the application of horizontal detection methods in remote sensing images, recognizing the significance of adapting existing techniques to the unique characteristics of remote sensing scenarios. Incorporating the circular smooth label, which is CSL method, to transform angle regression into a classification form, providing a solution to the periodicity challenge. Leveraging YOLOv5 as a baseline, the project aims to combine CSL to efficiently detect arbitrarily oriented targets. The goal is to enhance YOLOv5 model with an attention mechanism module to achieve fine-grained target detection in remote sensing images. The objective is to distinguish between instance classes and improve detection accuracy, particularly for small objects. The project aims for simplicity and efficiency to reduce hardware requirements while achieving meaningful results. The objective of the project is to implement YOLOv5 and its variants, which are YOLOv5S, V5CSL, V5X6, V8 for object detection in remote sensing images, and compare the performance of these YOLOv5 architectures to identify the most effective model for the given task, and analyze the performance metrics of the implemented YOLOv5 models on the chosen dataset. To implement the project, we need software and hardware requirements. And the software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. Coming to hardware requirements, operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above are required. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. In this step, necessary libraries and packages are imported into the project environment. We imported OpenCV for image processing, NumPy for numerical operations, frameworks like Torch and TensorFlow for deep learning, Seaborn and Matplotlib for visualization, Flask for web development. The next step is exploring the dataset. Here, images from the dataset are read, and the initial exploration involves plotting these images to gain an understanding of the dataset's content and structure. Coming to image processing, here we have converted images into blob objects, which is pre-processing images into a format that is suitable for input to the neural network. We define classes and declare the bounding boxes, which is preparing labels and bounding box information for the object detection. We converted array to NumPy array, which is ensuring compatibility with the NumPy, which is a popular numerical computing library. The next step is loading the pre-trained model. Here, pre-trained object detection model, which is YOLOv5 and its variants are loaded. Here, reading the network layers and extracting the output layer are crucial steps in gaining the model architecture. The next step is image processing. Here we have appended image annotation file pairs, which is combining images with their corresponding annotations for supervised training. We converted BGR to RGB, which is blue, green, red to red, green, blue, which is adjusting color channels to ensure consistency between image representations. We created the mask, which is preparing masks to highlight regions of the interest. We resized the image, which is standardizing image dimensions for model compatibility. The next step is data augmentation. Here we have randomized the images, where images undergo random transformations to introduce variety into training the data. We rotated the images, where images are rotated to diversify the dataset. Transforming the image, where additional transformations such as scaling and flipping are applied to augment the dataset. The next step is building the model. In this step, models are constructed. It involves defining the architecture, layers, and the parameters of the deep learning model for object detection. The next step is training the model. The model is trained on the prepared dataset using the backpropagation algorithm. During this phase, the model learns to detect objects based on the provided annotations. The next step is Flask framework with SQLite for sign up and sign in. Here, we set up a web framework using Flask to create a user interface. Here, we integrated SQLite for user authentication, allowing users to sign up and sign in securely. The next step is user gives input as images. User provide input in the form of images for object detection. The next step is pre-processing and model inference. Here, the given input images are pre-processed to prepare them for input into the trained model. The trained model is used to make the predictions and detect objects in the provided images. The next step is segmenting objects and adding bounding boxes. Here, identified objects are segmented and bounding boxes are added to highlight their locations in the images. The last step is displaying the final outcome. The pre-processed images with the segmented objects and bounding boxes are displayed to the user, providing a visual representation of the model's object detection capabilities. Algorithms which are used in the project are YOLOv5s, which is YOLOv5 small, represents the smallest variant of YOLOv5 architecture. First, we'll know what is YOLO. YOLO, which is you only look once, is a real-time object detection algorithm that processes images in a single forward pass through a neural network, providing rapid and efficient detection for multiple objects. It divides an image into a grid and predicts bounding boxes and class probabilities for each grid cell, making it a popular choice for real-time applications due to its speed and accuracy. YOLO has several versions, with YOLO v5 being one of the latest iterations, known for its improved performance and versatility. It is chosen as a baseline model to establish a starting point for object detection in the project. YOLO v5s is computationally more efficient compared to larger variants. It strikes a balance between speed and accuracy, making it suitable for initial experimentation and testing on the given dataset. YOLO v5s requires fewer computational resources, making it ideal for quick iterations and testing on various configurations without imposing a significant computational burden. Coming to YOLO v5 CSL, CSL refers to Circular Smooth Label. It is specifically designed to address challenges associated with angle regression in the object detection. The circular smooth label method is incorporated to transform the regression of angles into classification form. This helps overcoming periodicity challenges in angle regression, leading to more stable and accurate orientation predictions. YOLO V5 CSL is chosen to efficiently detect arbitrarily oriented targets in remote sensing images where the orientation of the objects can vary, making it crucial to accurately predict angles. YOLO V5 CSL's focus on precise angle estimation contributes to fine-grained object detection, which is essential for distinguishing similar targets and improving overall detection accuracy. As an extension, we employed other YOLO family models for enhanced performance and final prediction. Also, as an extension, we built the front end using Flash framework for user testing with the user authentication. We used performance metrics which are mean average precision, and recall to evaluate this project. So here we have performance comparison graphs for all the models built in the project. This is precision score comparison graph, where x-axis represents precision score for each algorithm and y-axis represents algorithm names. Similarly, we will have for other graphs also. Precision is a metric that measures the accuracy of positive predictions made by a model. It is calculated as the ratio of true positive predictions to the sum of true positives and false positives. Precision is concerned with the correctness of the positive predictions. This is recall comparison graph. Recall is also known as sensitivity and true positive rate. It measures the ability of a model to correctly identify all relevant instances of a class. It is calculated as the ratio of true positive predictions to the sum of true positives and false negatives. This is MAP, which is mean average precision comparison graph. It is the metric commonly used to assess the performance of the object detection models. It is calculated by averaging the average precision scores across multiple object classes. AP in turn measures the precision recall trade-off for a specific class by considering the precision at different recall levels. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder contains files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the model file which contains the algorithm information and that will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the sign-up file. This file is a database file used to store the user information. Now we have to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change to the code folder's path. So here we can observe that current directory is changed to the code folder's path. And here we need to type the command python space app.py to compile the app.py file. And now we need to click on enter. This will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. This is the local host and this 5000 is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser. And this web page is built by using the Flask framework. Here we can see a sign up link. We need to click on that. Here we can see all the registration details which are need to be entered. I have already signed up and I have an account in it. So we will directly click on login. Here we need to provide our username and the password to login. So I'm giving my username and the password. Now we need to click on login. We have logged in directly. And we are redirected to prediction page. Here we can see a choose file button. We need to click on that for uploading remote and aerial sensing images. So I'm clicking on choose file button. From the folder, I'm selecting the first image. Now we will click on open. And now we have to click on upload for detecting the objects in the image. Here we can observe that multiple objects are being detected from the image and the objects are parking lot, storage tank, and aeroplane. And each object has been drawn a bounding box around it with the probability score and with the name of the object. Probability score in object detection represents the model confidence level in correctly identifying and localizing an object, with higher scores indicating greater certainty in the prediction. Now we will upload one more image. Click on back arrow. Click on choose file. I'm selecting this image. Now click on open. And now we have to click on upload. Here we can observe that two objects are detected and the objects are crossroad and T-junction, and they are being drawn a bounding box around it with the probability score. Now we will upload one more image. Click on back arrow. Click on choose file. This time we will upload this image. Now click on open. And now we have to click on upload. Here we can see that only one object has been detected and the object is ship, and a bounding box has been drawn around the ship with the probability score. Now click on back arrow. Click on choose file to upload one more image. This time we will upload this image. Click on open and now click on upload. Here we can see that three objects are being detected and the objects are crossroad, ground track field and crossroad. And bounding box has been drawn around the object. Now click on back arrow. Click on sign out. In this way, if we upload aerial and remote sensing images to the system, then the system will detect objects in the images. Conclusion of the project. The project successfully addressed limitations in the existing object detection algorithms, extending their applicability to fine-grained objects in remote sensing scenarios. The introduction of an attention mechanism module in YOLOv5 enhanced the model's ability to perform fine-grained object detection. This improvement resulted in better recognition accuracy, especially for small objects without sacrificing computational efficiency. The integration of the Flask framework coupled with SQLite for user authentication established a user-friendly interface. This allowed users to input images and the system seamlessly processed and displayed the final outcomes, showcasing the practical application of the developed models. Researchers, industry professionals, and government agencies, militaries from enhanced object detection in remote sensing for improved analysis and decision making. The technology advancements also benefit technology developers and end users in remote sensing applications and the general public through increased accuracy and safety measures.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.